Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1671, minimum number of removals to make mountain array. This problem focuses on transforming an array into a valid mountain shape with the fewest removals. We'll break down the solution step by step, analyze its complexity, and discuss key takeaways. Let's dive in. In this problem, we are tasked with transforming a given integer array called nums into a mountain array with the minimum number of removals. So, what exactly is a mountain array? It is an array that meets two key criteria. First, it must have at least 3 elements. Second, there must exist an index I such that the elements before I form a strictly increasing sequence, and the elements after I form a strictly decreasing sequence. Essentially, the values rise to a peak at I and then fall, creating a mountain-like structure. Our goal is to determine the smallest number of elements we need to remove from nums to achieve this shape, and return that count. The input size n can range from 1 to 1000, so we need to keep efficiency in mind as we solve this problem. Let's start by examining a few examples to clarify the problem. In the first example, the array nums is 1, 3, 1. This array is already a valid mountain array because it has 3 elements. The sequence rises from 1 to 3, and then falls from 3 to 1. Since no elements need to be removed to satisfy the conditions, the output is 0. In contrast, consider a second example where nums is 2, 1, 1, 5, 6, 2, 3, 1. This array is not a mountain array because there are duplicates in the increasing section and the structure doesn't form a single peak. Here, we need to remove 3 elements to create the mountain shape. Let's explore how this is achieved. In the second example, 2, 1, 1, 5, 6, 2, 3, 1, one way to achieve a valid mountain array is by removing the elements at indices 1, 2, and 6. This leaves us with 2, 5, 6, 3, 1, which satisfies both conditions for a mountain array. The sequence rises strictly from 2 to 6 and then falls strictly from 6 to 1. Thus, the minimum number of removals required is 3. Now, let's examine another example to further solidify our understanding. Consider the array 4, 3, 2, 1, 1, 2, 3, 1. In the third example, 4, 3, 2, 1, 1, 2, 3, 1 is not a valid mountain array because the values decrease initially and the unique peak structure is missing. One possible way to fix this is by removing the elements at indices 0, 1, 3, and 4. This results in the array 1, 2, 3, 1, which is a valid mountain array, as the sequence rises from 1 to 3 and then falls to 1. The minimum number of removals in this case is 4. Finally, let's look at an example where the issue lies with duplicate elements. In the fourth example, the array 1, 2, 3, 4, 4, 3, 2, 1 initially fails the mountain array criteria because of the duplicate 4s, which break the strictly increasing and decreasing requirements. To fix this, we can remove one of the 4s, either at index 3 or 4. This results in the array 1, 2, 3, 4, 3, 2, 1, which is now a valid mountain array. The minimum number of removals here is 1. When tackling this problem, we must consider constraints such as the array size being up to 1000, which allows for solutions with time complexities like O, n squared, or O, n log n. We also need to handle edge cases, such as arrays that are already mountain arrays, arrays with all identical elements, and arrays with violations in the increasing or decreasing sequences, like 1, 2, 2, 1. Crafting an efficient solution will require careful thought about these scenarios. To solve the problem of finding the minimum number of removals to make a mountain array, we need to understand what constitutes a valid mountain array. First, it requires at least 3 elements. Second, the sequence must strictly increase up to a peak and then strictly decrease afterwards. This means the challenge boils down to identifying the longest subsequence within the array that satisfies these properties and then calculating how many elements need to be removed to achieve it. A brute force approach to solving this problem would involve generating all possible subarrays, checking which ones form a valid mountain, and tracking the number of deletions required. While this method is simple to implement, its complexity is a major drawback. Generating all subarrays takes O, n squared, and verifying the mountain properties for each subarray requires O, n, resulting in an overall complexity of O, n cubed. This makes brute force impractical for larger inputs, especially when the array size can go up to 10 to the power of 4. A more efficient strategy involves using dynamic programming to find the longest bitonic subsequence, or LBS. This represents the longest subsequence in the array that forms a valid mountain. Once we have the LBS, determining the minimum deletions is straightforward. It's simply the difference between the total array length and the LBS length. To compute the LBS, we break it into two parts. First, we calculate the longest increasing subsequence, or LIS, ending at each index. Then, we compute the longest decreasing subsequence, or LDS, starting at each index. The length of the mountain subsequence at any index is given by LIS I plus LDS I minus 1 to avoid double counting the peak. The maximum LBS across all indices gives the length of the largest mountain subsequence, and the number of deletions is the total array length minus this value. This approach has a complexity of O(n) squared, with a straightforward dynamic programming implementation for LIS and LDS, though it can be optimized further to O(n*log(n) using binary search techniques. While slightly more complex to implement than brute force, this method scales well to larger input sizes. Another approach is to use greedy techniques or two-pointer methods to directly locate peaks and calculate the number of removals required. This involves traversing the array to identify potential peaks, verifying the increasing and decreasing sequences around each peak, and tracking the length of the valid subsequence. From there, we calculate the number of deletions as the total array length minus the maximum valid subsequence length. This method has a time complexity of O(n) and is faster in practice. However, it can be error-prone, particularly when handling edge cases like multiple peaks or invalid sequences. Ultimately, the optimized dynamic programming approach is the most reliable and efficient for solving this problem. By focusing on the longest bitonic subsequence, we directly address the challenge of maximizing the valid mountain subsequence length. Although this approach requires additional space for LIS and LDS arrays, its time complexity of O(n) squared, or O(n*log(n) ensures scalability. While greedy methods may be faster, they lack the precision and generality needed for complex test cases. Brute force, on the other hand, is computationally infeasible. For these reasons, the DP-based solution strikes the ideal balance between efficiency, accuracy, and scalability, making it the best choice for this problem. To solve the problem of finding the minimum number of removals to create a mountain array, we first need to understand the characteristics of a valid mountain array. It must contain at least 3 elements, have a strictly increasing sequence that peaks at one value, and then strictly decreases after this peak. The key idea is to identify the longest subsequence of the array that meets these criteria. Once we know this length, we can calculate the minimum deletions required by subtracting the length of the longest mountain subsequence from the total length of the array. To achieve this, we break the problem into two parts. First, we calculate the longest increasing subsequence, or LIS, for each index, which gives the length of the increasing sequence ending at that index. Then, we calculate the longest decreasing subsequence, or LDS, for each index, which represents the length of the decreasing sequence starting from that index. Dynamic programming will help us efficiently compute both LIS and LDS values, which are essential for solving the problem. Once we have the LIS and LDS values, we can use them to construct potential mountain arrays. For any index in the array, we check if it can serve as a peak. A valid peak must have LIS and LDS values greater than 1, ensuring there are increasing and decreasing sequences on both sides of the peak. When a valid peak is identified, the total length of the mountain at that peak is calculated as the sum of LIS and LDS at that index, minus 1, since the peak itself is counted in both sequences. We track the maximum mountain length across all valid peaks. Finally, the minimum number of removals required is simply the total array length minus this maximum mountain length. This approach also accounts for edge cases. For example, if the array has fewer than 3 elements, it cannot form a mountain, so all elements must be removed. Similarly, for arrays that are strictly increasing or decreasing, no valid peaks exist, and all elements must be deleted except for 2 to form the minimum length mountain. There are several key insights that make this algorithm both efficient and robust. First, dynamic programming is used to calculate the LIS and LDS values. By iterating over the array and building upon previously computed results, we ensure that the LIS and LDS arrays are computed in O(n) squared time. This is far more efficient than recalculating subsequences for each index. Second, pre-computing the LAS and LDS arrays avoids redundant calculations, which makes the process both faster and simpler to implement. Another critical insight is the condition for valid peaks. For a peak to be part of a mountain, LAS and LDS values at that index must both be greater than 1. This ensures that the sequences around the peak are strictly increasing and decreasing, rather than flat or invalid. These insights form the foundation of the algorithm's efficiency and correctness. The algorithm uses several key data structures to efficiently calculate and validate the mountain arrays. The LAS array stores the length of the longest increasing subsequence ending at each index. For example, if the array is 2, 1, 4, 7, 3, 2, the LAS values might look like 1, 1, 2, 3, 2, 2. This shows how the sequence grows as we move through the array. Similarly, the LDS array stores the length of the longest decreasing subsequence starting at each index. For the same array, LDS values might be 1, 1, 1, 3, 2, 1, indicating how the sequence shrinks moving backward. Finally, a peak tracker helps keep track of the maximum valid mountain length found so far. These data structures work together to calculate and validate potential mountain arrays efficiently. To calculate the LIS values, we iterate through the array for each index. For any index I, we look at all previous indices j where j is less than I. If the element at index j is smaller than the element at index I, we update LIS I as the maximum of its current value in LIS j plus 1. Similarly, LDS values are computed in reverse. For each index I, we check all subsequent indices j where j is greater than I. If the element at index j is smaller than the element at index I, we update LDS I as the maximum of its current value in LDS j plus 1. After calculating LIS and LDS, we validate peaks by ensuring that LIS I and LDS I are both greater than 1. This guarantees that the sequences around the peak are strictly increasing and decreasing, respectively, forming a valid mountain. Finally, let's analyze the complexity of the algorithm. The time complexity for computing both LIS and LDS is O(n squared), as we iterate through the array and compare each pair of indices. Thus, the overall time complexity of the algorithm is O(n squared). In terms of space complexity, we use two arrays, LIS and LDS, each of size n. These arrays take O(n) space, resulting in a total space complexity of O(n). This balance of time and space complexity ensures that the algorithm is efficient and scalable for moderately sized inputs, making it a practical solution for the problem. In this solution, we aim to minimize the number of removals needed to transform the input array into a mountain array. A mountain array starts with a strictly increasing sequence, peaks at a single element, and then decreases strictly. To solve this, we use a dynamic programming approach to calculate the longest increasing subsequence, LIS, and longest decreasing subsequence, LDS, for every element. First, we calculate the LIS using a nested loop. For each element in the array, we check all previous elements and update the LIS value if the current element extends the increasing sequence. Next, we compute the LDS in a similar way but iterate the array in reverse. This ensures that we capture the decreasing sequence for each element. Once we have both LIS and LDS values for every index, we compute the maximum length of a valid mountain array by considering only indices where both LIS and LDS are greater than 1, indicating a peak. The mountain length at any peak is calculated as LIS I plus LDS I1, accounting for the peak being double counted. Finally, the minimum number of removals is given by subtracting the maximum mountain length from the total array length. This ensures that we keep the longest possible mountain array while removing the minimum number of elements. The algorithm runs in O(n squared) time due to the nested loops for LIS and LDS computation. Here, we begin by importing the necessary libraries and defining our solution class with the method minimum mountain removals. The goal is to calculate the minimum number of elements we need to remove to form a mountain array, which is defined as an array where there exists at least one peak element, and the elements strictly increase before the peak and strictly decrease after it. First, we calculate the longest increasing subsequence, or LIS, from left to right. We initialize an array LIS with all elements set to 1, as each element is itself a subsequence. Then, for each element in the array, we compare it with all previous elements. If a previous element is smaller, we update the LIS at the current index to the maximum of its current value and the LIS of the previous index plus 1. This ensures that the LIS array stores the length of the longest increasing subsequence ending at each index. Next, we compute the longest decreasing subsequence, or LDS, but this time from right to left. Similarly, we initialize an array LDS with all elements set to 1. We iterate backward through the array, and for each element, we compare it with all succeeding elements. If a succeeding element is smaller, we update the LDS at the current index in the same manner. By the end of this step, the LDS array reflects the length of the longest decreasing subsequence starting at each index. Now that we have both the LIS and LDS arrays, the next step is to identify the maximum valid mountain array length. To do this, we iterate through the array, skipping the first and last indices since a mountain cannot start or end at these positions. For each index, we check if both LIS and LDS at that index are greater than 1, which ensures the presence of both an increasing and decreasing sequence. If this condition is met, we calculate the total length of the mountain at this index by summing the LIS and LDS values and subtracting 1 to avoid double counting the peak element. We then update the max mountain length to keep track of the longest mountain found so far. Finally, the minimum number of removals required to form a mountain array is simply the total length of the array minus max mountain length. This gives us the result, which we return from the method. By combining the LIS, LDS, and the final computation, we efficiently solve the problem within a reasonable time complexity. To solve the problem, we start by calculating the longest increasing subsequence, or LIS, for the given array. Initially, each element in the LIS array is set to 1, because the minimum subsequence length for any individual element is itself. We then iterate through the array, comparing each element with all previous elements to see if it can extend an increasing subsequence. For instance, when we reach index 3, we compare the value 5 with all earlier values 2, 1, and 1. Since 5 is greater than 2, we update LIS 3 to 2, indicating that the subsequence 2, 5 has length 2. Similarly, at index 4, the value 6 continues the subsequence 2, 5, 6, updating LIS 4 to 3. This process continues for all indices, resulting in the final LIS array, which represents the length of the longest increasing subsequence ending at each index. Next, we calculate the longest decreasing subsequence, or LDS, starting from the end of the array. Each element in the LDS array is initialized to 1, as the smallest subsequence for any individual element is itself. We iterate backward through the array, comparing each element with all subsequent elements to see if it can extend a decreasing subsequence. For instance, at index 6, the value 3 is greater than the value 1 at index 7, so we update LDS 6 to 2, forming the subsequence 3, 1. At index 5, the value 2 also forms a valid subsequence with 1, updating LDS 5 to 2. Similarly, index 4 forms a subsequence 6, 2, and index 3 forms 5, 2, 1, updating their respective LDS values. By the end of this process, the LDS array provides the length of the longest decreasing subsequence starting at each index. Now, we use the LIS and LDS arrays to find the maximum valid mountain length. A valid mountain peak must have both LIS, I1 and LDS, I1, meaning it supports both an increasing and decreasing subsequence. We iterate through the array, checking these conditions. For example, at index 3, both LIS and LDS values are greater than 1, so we calculate the mountain length as LIS 3 plus LDS 3, 1, which equals 4. Similarly, index 4 also forms a valid mountain of the same length. After identifying all valid mountains, the maximum mountain length is determined to be 4. To calculate the minimum number of removals needed to form this mountain, we subtract the maximum mountain length from the total number of elements in the array. Given that there are 8 elements, the minimum removals required are 8 minus 4 is equal to 4. In this example, the array consists of a strictly decreasing sequence, meaning there are no increasing subsequences. As a result, the LIS array remains 1, 1, 1, 1. The LDS array, however, captures the entire decreasing sequence as it is, resulting in 4, 3, 2, 1. Since no index in the array satisfies the condition of having both LIS, I1 and LDS, I1, there is no valid mountain in this sequence. Consequently, the entire array must be removed to meet the problem's requirements. With 4 elements in total, the output is 4. Here, the array contains 3 elements in the form of a valid mountain, 1, 3, 1. We first compute the LIS, which shows that the subsequence increases to a peak at index 1, resulting in LIS equals 1, 2, 1. Similarly, the LDS captures the decreasing sequence from the peak, giving LDS equals 1, 2, 1. Since index 1 satisfies the condition of having both LIS, I1 and LDS, I1, it forms a valid mountain with a total length of 3. As the entire array already forms a mountain, no elements need to be removed, resulting in an output of 0. We start by analyzing the time complexity of the code. The first step involves computing the longest increasing subsequence, or LIS. Here, we use a nested loop structure where the outer loop iterates over each element I from 0 to n1, and for each I, the inner loop processes all previous elements j from 0 to I1. Within the inner loop, we check if nums, j, is less than nums, I, and update the LIS array accordingly. This nested iteration results in n squared, overall time complexity for this step. Similarly, in the second step, we calculate the longest decreasing subsequence, or LDS, but this time the outer loop runs in reverse, iterating I from n1 to 0, and the inner loop processes all elements j from n1 down to I plus 1. The logic is equivalent to the LIS calculation, and as such, this step also requires n squared time. Lastly, the third step is to find the maximum valid mountain length. This involves a single loop iterating I from 1 to n2, checking conditions for LIS and LDS values, and updating the maximum mountain length. Since it's a single loop, this step runs in n time. The fourth step is to calculate the minimum number of removals. This step is straightforward, involving a simple calculation, n max underscore mountain underscore len. Since this is a constant time operation, it contributes 1 to the complexity. Combining all the steps, the LIS and LDS computations dominate the overall time complexity, each requiring n squared. The subsequent steps, including the single loop for finding the maximum mountain length and the constant time calculation, contribute only n and 1, respectively, which are negligible in comparison. Therefore, the overall time complexity of the solution is determined to be n squared. Now, moving on to space complexity, the input list nums of size n contributes n space. Additionally, we use 2 auxiliary arrays, LIS and LDS, each of size n, which also contribute n space. Finally, temporary variables such as max underscore mountain underscore len, I, and j consume constant space, or 1. Adding up these contributions, the total space complexity is dominated by the input storage and the auxiliary arrays, giving us a final space complexity of n. To better understand the efficiency of the optimized approach, let's compare it to a brute force method. A naive brute force solution would involve generating all possible subsequences of the input array to check if they form valid mountain arrays. Since generating all subsequences has an exponential complexity of 2 to the power of n, and verifying each subsequence would add additional overhead, this approach becomes infeasible for large input sizes. On the other hand, the current optimized solution leverages dynamic programming to calculate LIS and LDS in n squared time, which is a drastic improvement. Additionally, the space complexity is reduced to n, since we only use 2 auxiliary arrays, making this approach both efficient and scalable. Let's now analyze the best, average, and worst-case scenarios for this algorithm. In the best case, the input array is already a valid mountain array. Even in this scenario, the LIS and LDS arrays will still be calculated, as the algorithm does not include early termination for this case. The time complexity remains n squared, though the constant factors may be slightly smaller due to fewer updates to the arrays. In the average case, which represents a random input array, the LIS and LDS calculations proceed normally, and the time complexity is again n squared. Finally, in the worst case, the input array contains no valid mountain subsequence. Here, the LIS and LDS calculations are performed fully, iterating through all pairs of elements without any shortcuts. The time complexity remains n squared in this case as well. Regardless of the input, the algorithm's performance is consistent, with the dominant factor being the LIS and LDS computations. To solidify our understanding, let's validate the big O time complexity mathematically. Both the LIS and LDS calculations involve nested loops. For each iteration of the outer loop, the inner loop runs approximately n/2 times on average, leading to a total of n*n/2 iterations. Simplifying this gives n², which is asymptotically equivalent to O(n²). The subsequent operations, such as the single loop for finding the maximum mountain length and the constant time calculation for minimum removals, do not affect the overall complexity. Therefore, combining all the steps, the final time complexity is confirmed to be O(n²). On the space complexity side, the input array and auxiliary arrays dominate the memory usage, each contributing O(n). As a result, the total space complexity is O(n), making this solution both time and space efficient for the problem at hand. When solving this problem, it's critical to avoid some common mistakes. First, remember that a mountain array must have both an increasing and a decreasing sequence with exactly one peak in between. This means the peak cannot be at the start or end of the array, and there shouldn't be any flat sections where consecutive elements are equal. To fix this, ensure that the peak is strictly between the increasing and decreasing subsequences and verify the absence of flat sections. Another frequent issue is incorrect computation of the longest increasing subsequence, or LIS, and the reverse longest increasing subsequence, or LIS. These are core to many solutions, but errors in handling boundary conditions or combining LIS and RLIS values correctly can lead to invalid results. It's important to compute LIS and RLIS for all indices carefully while ensuring the peak is valid. Finally, overlooking edge cases can cause major problems. For example, arrays with fewer than 3 elements or arrays where no valid peak exists, such as 1, 2, 2, 1, must be handled explicitly. Always check for these scenarios before proceeding with the main algorithm to prevent runtime errors or incorrect outputs. Another challenge is inefficiency. Brute forcing all possible peaks results in O(n³ complexity, which is far too slow for large inputs, such as arrays with 10,000 elements. Instead, optimize using dynamic programming, which brings the complexity down to O(n², or even better, binary search, which achieves O(n log n) for LIS and RLIS. Additionally, ignoring problem constraints can be a pitfall. For example, a solution that works for small test cases might fail on larger ones because of a time limit exceeded error. To avoid this, always analyze the constraints and optimize your approach accordingly. From an interview perspective, this problem highlights several key areas. First, it demonstrates the importance of dynamic programming patterns, especially bidirectional DP like LIS and RLIS. The peak element acts as a crucial pivot, so it's essential to explain how you ensure it satisfies all mountain array properties. Furthermore, be prepared to discuss optimization trade-offs between O(n² and O(n log n) solutions. Finally, showing your ability to identify and handle edge cases, such as short arrays or arrays without a valid mountain, is a great way to stand out. This problem also connects to several related challenges. For instance, LeetCode number 300, longest increasing subsequence, is the core concept used here. LeetCode number 673, number of longest increasing subsequences, builds on LIS concepts and is another useful problem to explore. LeetCode number 376, wiggle subsequence, introduces peak and valley constraints similar to this problem, and LeetCode number 845, longest mountain in array, is a simpler variation where the goal is to find the longest mountain in a single pass. When it comes to alternative approaches, dynamic programming with O(n²) complexity is a straightforward method. It uses nested loops to compute LIS and RLIS and is easier to implement, but it might result in time limit exceeded errors for very large arrays. For better efficiency, binary search offers an O(n log n) solution by leveraging data structures like Fenwick trees or segment trees to compute LIS and RLIS. However, this method requires more advanced techniques and is harder to implement during time-constrained interviews. Lastly, for specific variations of the problem, a sliding window approach can simplify the solution to O(n), but it doesn't generalize well to all cases. Understanding when to use each approach and their trade-offs can help you navigate both coding challenges and interviews effectively. Great job! We've completed LeetCode problem number 1671 and learned how to approach sequence transformation problems using dynamic programming. Remember to keep practicing and exploring similar challenges to strengthen your problem-solving skills. Thanks for watching, and we'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!